Greetings, my name's Larry Theller. I'm a GIS specialist with the Purdue University Department of Agricultural and Biological Engineering. I'm one of the project managers on a model that we've developed and that we have connected to the Tipping Points planning system. The point of the model, long-term hydrologic impact, would be to look at the impact over many years of changing land use, seeing how much water goes in the soil from the land use. The calculations not only tell you the proportion of the water that's being infiltrated into the soil, but it also talks about the chemistry of the water that's running off into the ditch. For example, if I pave a farm field, I have a parking lot, I'm going to pick up oil and gas when the water goes over the parking lot. If it's a farm field, I'm going to pick up a little fertilizer when it goes over. So we have some assumptions we make about the chemistry, as well as assumptions we make about how much water is moving around. This little cartoon brings out the concept then. So in the top image, it's raining on forest land or a wetland or a field, and a large amount of the rainfall soaks in the ground. That's the normal concept. And it depends on if you have rocky soil, but that's the general concept. As we start building, you can see the gray slabs moving across the earth profile. We get less and less rainfall infiltrating into the soil, which means now we have more and more water moving across the surface of the earth. And that's the underlying concept of the model. So we're making these basic assumptions. The water is flowing across the surface, and that means the surface. So we don't include storm drains, we don't include tile drains. That's really complexity beyond what our model can handle. Which means in an urban setting, when you know all the water is being taken through tunnels to the sewage treatment plant, then we're probably giving numbers that need to be adjusted because we're assuming it's all flowing down the hill into the valley. That's how our model would work. We assume the water is equally spread across the landscape. We don't include the stream. The water doesn't fall in the stream and disappear. It's just X amount of rain over the whole valley leads to X amount of runoff over the whole valley. We have a condition in the model called average antecedent moisture, and that basically means the ground in our model is not frozen. It's accepting the water. So if you've had 20 days of rain and you run one of these models, then you really won't have any more water go in the soil because it's already saturated. And so in a world like that, you would have to put in a value for how saturated the soil is. Because we're using real observed data, we're not using anything in the winter, so the ground's never frozen, because that would greatly change our calculations. All the water runs off on frozen ground. So basically in our model, it's a day in June every day that we run our model. And the rainfall is evenly spread. We use a rain gauge for every county, and we use one number for that county. If you've been on a farm, say in a big storm, and you have a couple of rain gauges, you know that rainfall is not that even. So that's an assumption, but we have to make a few assumptions. The world of low impact development, or sometimes also known as green infrastructure or GI development, is really kind of an approach to land use planning or to land development, which tries to mimic the pre-development site hydrology, or at least, if not mimic, at least it tries to take us back towards pre-development site hydrology. So that the standards that you do for that, you reduce the volume of runoff, which means if you have a house and you think of all the water that falls on your roof, right now might go through a gutter under the yard, and from the yard onto the street, from the street into the sewer, and that's the part we want to reduce. So you can decentralize that runoff. You can put it into small rain gardens, smaller retention areas. That alone will improve the water quality. The less water that you have running across pavement, the less contamination you pick up. And it also encourages groundwater infiltration. So when we're running the L-THIA model, when we're running the tipping points planner and we're connected to the L-THIA model with the paint tools, the kind of questions you're asking yourself are these on the screen. So you're probably trying to compare different ways to reduce the imperviousness. Porous pavement reduces the imperviousness of an area, or a green roof, or porous sidewalks. So the tools are built to let you have some choices, and you can do things over and over. So we could say, let's say we change our zoning and we say that all driveways are going to be porous in this new subdivision. So I could model that with and without that one change. And then I could say to the developer, if you do this, we know that those driveways will cost you more, but on the other hand, you will reduce the amount of water that you have to take care of with some kind of detention or something by 10 million gallons or whatever the number is. So part of the tool design was to let land use planners have some tools that they can take into a discussion with builders, developers, or others to show what alternatives not only cost, but what the possible benefits are. We allow you in the model to look at what happens to soil when one of these, the really large developments typically compact, at least accidentally, compact the soil to change the way it behaves. So in the model you can show that. How are you rewarded if you conserve functional or sensitive landscapes? The non-point source pollution calculations can show that you are moving towards some kind of regional goal. Let's say that your whole region has been told they need to reduce the amount of phosphorus in the river. You can model future development to see what the phosphorus reductions might look like using these tools. And in the end, you're encouraged to minimize land disturbances. Most times the model is going to say that the less paving and construction you do, the better the water quality is going to be in the area. So that you can model high density housing versus low density housing. Is 500 people in 1/8 acre lots going to be better than 500 people in 2 acre lots? They're going to spread out over a much larger area. So overall, the whole point of this was to help people anticipate the need for these practices, and then to actually show this, give you some form of support for practices that maybe you want to consider as you evaluate scenarios one way or another. Currently in the tipping points planner, you're able to basically draw on the screen the 5 practices that are in the upper box. And we're proposing future additions to bring in some more of these. So the top 5 are some pretty common GI or LID practices. Green roofs, bioretention system, that could be called rain garden sometimes also, porous pavement, rain barrels. So these are, the impact of these are computed as if they are spread through all the houses in the area you've drawn. So you don't dot a house and say, I've got 1 rain barrel, what's that going to get me? Because really that won't get you anything. But you can draw a box on 500 acres and say, we're going to change the zoning, the new place is going to have porous pavement, and what's the impact? And the computer then says, okay, 500 acres, 2 acre lots is going to have certain square footage of pavement, we'll make all that porous, what's the benefit? And that'll be the answer.